Hey everybody, welcome to Chapter 6, Section 2, Properties of Rational Exponents and Radicals. This is part 1 of a two-part section. So right up here at the top, I just screenshotted some stuff from your textbook, and these are all the properties of rational exponents and properties of radicals. So, exponents have the powers, and the radicals have the radical, or what you might call the square root symbol. But of course, it's not always square rooting. That's why it's called the radical. So refer back to this as needed. I'm not going to read the whole thing to you. I'm just going to go through these examples and go over them, just on a case-by-case basis. So here you have 7 to the 1/4 times 7 to the 1/2. If you have the same base, that means you are adding your exponents. So I'm doing 1/4 plus 1/2. So it helps to know your least common denominators. I know that 1/2 can be rewritten as 2 over 4, because 2 is half of 4, so it's not too bad. And so I know 1/4 plus 2/4 is 3/4. So 7 to the 3/4 power is my final answer. All right. That's all you have to do. I'm not looking for the, typing it into the calculator and getting that answer. Okay. So what we have here is 4 to the 5th times 3 to the 5th. So we have like exponents. Like exponents, but different bases. So what we can do is we can still multiply these together. This is going to be 12 to the 5th power. And you can only do that because the exponent's exactly the same. So I'm doing 12 to the 5th power raised to the negative 1/5 power. So if you were raising a power to a power, you multiply your exponents. And you know you're raising a power to a power because there's nothing written right next to the negative 1/5. Like there's not a 12 or there's not a number, there's no base to it. That's how you know you're raising a power to another power. So to show my work, I'm doing 12 to the 5th times negative 1/5, and that's going to be 5 times negative 1/5 is negative 1. Okay, so what do negative exponents mean? I've gone over this in the 6.1 actually. It means fractions, so that is going to equal 1 over 12 to the 1st power, or simply just 1 over 12, and that's actually the final answer. Okay, so here with example 3, I have different exponents, so I'm not going to multiply the 6 times 4. What I'm going to do is I'm going to write this as 6 to the 1/2 times 2 times 4 to the 1/3 times 2, and let's see here, 1/2 times 2 is 1, so 6 to the 1st power times 4 to the 1/3 power times 2 is 2/3, so 6 times 4 to the 2/3. And really, it can't simplify beyond that other than to just drop the 1, because you never have to write anything to the 1st power. If it's just a regular number, you know it's to the 1st power. So this is basically as simplified as it can get, writing 6 times 4 to the 2/3 power. Okay? So with number 4, I'm dividing. I have the same base, but I have different exponents. And if you're dividing with the same base and you have exponents with them, you subtract the powers. So if that's 5, I can rewrite that as 5 to the 1st power. And so I can rewrite this as 5 to the 1st power minus to the 1/3 power. Okay, because they're both 5. And then, well, let's do least common denominator. What number over 3 equals 1? And that's 3. 3 divided by 3 equals 1. I kind of pose that question kind of awkwardly. So this is 5 times 3 over 3, because that makes 1. Least common denominator stuff. Minus 1/3. So 3/3 minus 1/3 is 2/3. So the final answer here is 5 to the 2/3 power, and that's it. So this one you have 42 to the 1/3 divided by 6 to the 1/3, and then the second step's actually done for you. You can just rewrite that as 42 over 6 to the 1/3, and then they're being raised to the second power. So you're raising a power to a power. So let's take care of this. What's 42 divided by 6? That's 7. So this says 7 to the 1/3 raised to the second power. So if you're raising a power to a power, multiply them. So what is 1/3 times 2? Well, that's just 2/3. So the final answer is 7 to the 2/3 power. Okay? So moving on to the next section, these are properties of radicals. If you have the same radical, I'm doing the third root of each number, then you can multiply. You can do this as the third root of 12 times 18, and 12 times 18 equals 216. So I can rewrite this as the third root of 216, and I know the third root of 216 is 6. So that's all there is to that. So for this next one, I have 80 over 5. It would be really easy to simplify if 80 or 5 had a fourth root, and unfortunately neither one of them does. So what I recommend doing is pulling up a list, like going to typing in x to the fourth power using your calculator, and seeing what has a fourth root. Okay, so you'll see that 81 has a fourth root, but not 80. But does 16 go into 80? And yes, it does. So the first thing I'm going to do is I'm going to rewrite this as the fourth root of 16 times 5 over 5. So here's the thing. I have 5 over 5. Well, that's going to cancel. So I have the fourth root of 16 left over. And what is the fourth root of 16? It's 2. So the final answer is just 2. So it's kind of a crazy looking problem, but yeah, that's really all there is to it. So similar thing on number 3, I'm taking the third root of 135. This problem would be really easy if 135 had a cube root, but it doesn't. So what you should do is type in x to the third power and pull up that list of perfect cubes, and then you need to start dividing. Can you do 135 divided by 8? Can you do 135 divided by 27, divided by 64, divided by 125, divided by 216? Really, you want to take the biggest one that you can divide it by, so you might want to go in reverse order, like starting with 125, but that's not going to make a whole number. 135 divided by 64 isn't going to make anything nice. Well, 135 divided by 27 is... 135 divided by 27 makes 5. So I'm going to rewrite this as the cube root of 27 times 5. All right. And we know the cube root of 27 is 3. So I'm going to take that 27 and just write 3. And then I don't know the cube root of 5. Well, I could type it in the calculator and then I'd know, but we're trying to do this without using the calculator, or which is kind of funny because I told you to use a calculator to get the x to the third thing, but the idea is we're simplifying it, we're not equating it, we're not typing it into the calculator to get the decimal approximation. Okay, that's really what we're doing. But yeah, that cube root of 27 made 3, so put that on the outside, leave what's left over on the inside, and that's all there is to it. This one's not so bad. You have the square root of, or the fourth root, excuse me, of 10. And so you have different coefficients. I can write a 1 on the outside. What's 1 plus 7? That's 8. So this is 8 times the fourth root of 10. And really that's all it can simplify to get, alright? I can't do anything beyond that. There is no number, there are no factors of 10 that have fourth roots. So that's actually all there is to number 4. So number 5 is kind of unique in that they're both being fifth rooted. So you could rewrite it as one fraction, the fifth root of 7 over 8. Unfortunately, that wouldn't be acceptable for the final answer. What you need to do is, um, it's kind of improper to have a radical on the bottom of a fraction. So if we're going to simplify this, we need to get something to the fifth power, ideally on the bottom, um, so that way we could take the fifth root of that number and we won't have a radical on the bottom. So what I'm going to do is I'm going to pull up my list of fifth roots and just leave that right there. And so let's see here. 8 times 4 is 32. So and if I multiply 8 times 4, I'll get 32, and that's the next closest fifth root that 8 can go into. You want to do that. So don't worry about this. What we're going to do is we're going to write the fifth root of 7 over the fifth root of 8. And I'm going to multiply this not really by 4, but the fifth root of 4, because you have to keep the same base or the same radical. Yeah. And remember, this is just straight out of least common denominator stuff. What you add to the bottom of the fraction, you must add to the top of the fraction as well. And so, again, the purpose of doing that was so we'd have a number on the bottom that could be fifth rooted. And so 7 times 4 is 28. And so this is 28 to the fifth root over 32 to the fifth root, or the fifth root of 32. I'm saying it kind of weird. And we know the fifth root of 32 is 2. So I'm going to write equals the fifth root of 28 over 2. And that is the final answer. This one here, it's pretty easy. It's 2 times 8 to the 1/5 and 10 times 8 to the 1/5. You don't even have to distribute this. Just combine 2 plus 10. That's 12. This is going to become 12 times 8 to the 1/5. And that's actually going to be your final answer, because I couldn't just combine them and do 12 times 8 and write it as, what is that, 96? Yeah, that's 96. I can't write it as 96 to the 1/5 because this is 12 to the first power times 8 to the 1/5 power, so they have different exponent, different powers, exponents. So this is actually the final answer, writing as 12 times 8 to the 1/5. All right? Moving on to number 7, the last example. You have the same base, or no, you have different bases, but you have the same, what am I trying to say? You have the same radical, but it's actually not the same thing as just doing, well, what's 54 minus 2? That's 52. If you type it into the calculator, and doing, here I have it displayed as 52 to the 1/3 power, because that's the same thing as taking the cube root of something. Here I have 52 to the 1/3. You can see it makes a different number than just typing in 54 minus 2 to the 1/3. So what you should do is, what is a perfect cube that is inside 54? So if it helps, pull up that perfect cube list, all right, and 54 divided by 27 is 2. And so that's kind of nice, because that means I can turn this into 3 times 54. No, not 54. 27 times 2 minus the cube root of 2. Well, I know the cube root of 27 is 3, so I'm going to write this as 3 times the cube root of 2 minus the cube root of 2. Well, I have 1 cube root of 2 right there. So what's 3 minus 1? That's 2. So I'm going to rewrite this as my final answer is 2 times the cube root of 2. And that's really going to be it. I'm just going to rewrite this 3 to look maybe more like a 3. And I think I made it worse, but you know what? I'm okay with that. This is the final answer. That's going to conclude the notes. Thanks for watching. Bye.